Hello everyone, I'm Dr. Priya Hasan and I've been requested to give you another talk on astronomy, which is something I always love to do. And so here I am once again. And today, because I was requested for a second talk, I've picked up a talk which is a mix of, it's called Seven Big Questions in Astronomy, so that it covers the whole field of astronomy from exoplanets to cosmology. And I hope that would be nice and interesting for you all. So let's start with that. And yeah. So, like I mentioned, is that because I wanted to cover the broad spectrum of different topics in astronomy, I picked up a thing which actually is a mix of everything, the 10 biggest questions about the universe and how we are trying to answer them. Because that's the important aspect as to how are we actually trying to address these questions. Like you earlier heard in my talk, I teach at the Maulana Azad National Urdu University in Hyderabad, and that's my email. You can always write to me if you have any questions. So let's start off with the first big question. No, this is not yet the first big question. This is just to let you know what is astronomy, astrophysics, and cosmology. So it basically what we do in that is a study of celestial bodies, right? Celestial objects. It is yeah, it is, and basically it's a science that employs the methods and principles of physics and chemistry in the studying of astronomical phenomena. That's the big difference between astronomy and, for example, astrology. In astrology, also you're studying celestial objects, but you do not employ the principles of physics and chemistry, right? And mathematics, actually. Cosmology is the study of the origin, development, the structure, history, and future of the entire universe. Okay, that's the difference between these three things. So let's see the 10 big questions, and the rest you can ask. So the 10 big questions which I've listed over here. First of all is, can an asteroid fall on the Earth? 2. How did we find our place in the universe? 3. Are planets other than the solar system, which we call exoplanets? Is there 4? Is there intelligent life in the universe? 5. Is what are black holes? 6. What's in the center of our galaxy? 7. How did the universe begin? 8. What is dark matter? 9. What is dark energy? And 10. Is space tourism the future? Okay, so these are just some selected questions. You could have many more, but I just selected this to cover the whole range of astronomy. So let's start off with question number 1. Question number 1 is, can an asteroid fall on the Earth? So, well, we know that June 20th is actually celebrated. It was declared by the United Nations as the Asteroid Day, and it's celebrated all over the world. And it's basically a day to basically build up public awareness of asteroid impacts. So what you see in the background is a picture of this is Tunguska, this is in Siberia. And over here you actually had an asteroid which impacted in 1908. And therefore this asteroid date is the same date as that, June 30th, 1908. And it is to mark the date of that. Because you can see the impact even today. You can see in this whole region there's no plants, there's no nothing. The whole thing is still, even after 100 years, under the impact. So let us try answer the question that can we actually be impacted. So actually we all know that about dinosaurs, and the dinosaurs actually went extinct 65 million years ago, basically because of there was actually an asteroid which hit it. The asteroid was the size of about 10 to 15 kilometers. And as per, we actually have good enough evidence for it, because in the geological record, this is called the KPG event, or the Cretaceous Paleogene event. And you basically have a thin layer of sediment which is found in rocks belonging to that period, which actually is composed of material which is high levels of iridium, which is more common in asteroids than in the Earth's crust. As well as we actually have a crater. We have an impact region which is in the Gulf of Mexico's Yucatan Peninsula. That is actually the region where we actually think this impact to take place, right? In India, we have the Lonar Lake, which is in Maharashtra, and this is actually, you can see it's a perfect circular thing. It's an impact thing, perfect circle. Look at this. This is now, it's obviously with time, it's gotten filled with water. So this is called, it's a lake, a Lonar Lake. But you can see that this is a clear circle, and it's one of the first hypervelocity, one of the 4 known hypervelocity things, which is there on the Earth. The other ones, other three structures are in southern Brazil. You have a mean diameter of about 1.2 kilometers, and the meteor rim is about 1.8 kilometers in diameter. Right? So that's a perfect circular impact. So let us see what is the frequency. So every day the Earth is basically bombarded with more than 100 tons of dust. Once a year, a car-sized asteroid hits the Earth's atmosphere, creates a fireball, but what happens is when it enters, there's so much of friction that it like burns up in the higher atmosphere. Every 2000 years, you have a size of a football field, which can actually cause significant damage. And once every few million years, you can actually have the kind that led to the dinosaur extinction, which is really huge, and this is 10.5 to 15 kilometers across. So typically, if the rocks are smaller than 25 meters, right, then most of them they burn up in the Earth's atmosphere, and we don't need to worry about it. But if it is larger than 25 meters, up to 1 kilometer, it would likely cause damage in the local area, in the impact area. But if it has a size larger than 2 kilometers, 1 or 2 kilometers, then you could have worldwide effects. I didn't speak about it, but typically in the dinosaur event, see, it's not that the asteroid fell on the heads of dinosaurs. That's not the thing. The problem is that because of the impact, you had a lot of dust which came out in the atmosphere. Okay, and that dust covered a very high level, right, on the ground. Now, how does the food chain work? You basically have, at that time, you had dinosaurs which fed on plants, right? And then there were dinosaurs which fed on the dinosaurs which fed on plants. So what happens when you have this high level of dust in the atmosphere? Sunlight doesn't come in, right? So the plants which they don't survive because the sunlight doesn't come in. So those plants die out. So the dinosaurs which feed on the plants, they die out, and therefore the dinosaurs which feed on the dinosaurs which feed on the plants, they also die out. So what happens? Don't think of this as an event that the asteroid fell and you had like a bomb blast. No, the problem is because of this amount of dust that is created in the atmosphere, right? And that is what actually led to the extinction of dinosaurs, because the whole food chain got broken, right? The plants did not survive because of that. The dinosaurs which survived on plants did not survive, and in turn the other dinosaurs, right? So it's a chain process like that which takes place, due to which you have a complete extinction, right? So that is the kind of effect which this impact would actually have. So we have asteroids in the solar system, and there's an asteroid belt between Mars and Jupiter, but they are far from us. They could be very large also, but they are far from us. But if due to some reason they are perturbed from their orbit by something, that's when they can come and enter into the Earth's orbit, right, close to the Earth. So what are these asteroids? Where do they come from? So here you can see a video. This is a video of the formation of our solar system. And you can see that when our solar system formed, you basically, one minute, I will just do a certain thing. I think I have not enabled content. So I'll do that. I'll come back here and I'll do this. So what happens is, this is the video of the formation of our solar system. It is not working. But you can see that this is the protoplanetary disk from which the solar system formed. And what happens is, this is the young sun forming, you have this material around this which actually accretes to form planets. And that is when they basically, you have this accretion process taking place. And while the accretion took place, you did not have all the material forming into planets. So the rest of it actually formed what are called asteroids. So you can see it in this picture. Okay, it's not coming in this video. 1 minute, I'll just try to this thing. I don't know why it's not. Okay, let's see if this plays. It for some reason doesn't want to. Okay, let it be. Okay, yes. So here's the solar system in formation, right? Like I told you, you have the planets, etc., forming at different locations, and they coalesce together to form their planets. So you can see already the orbits are forming. Here the sun is formed. This is the trigger of nuclear reaction, because the sun is born when it starts doing nuclear reactions, and then you have these different planets forming at different distances. But you see that there's always some amount of debris material which did not go into the formation of a planet, and that is the material between these planets, which actually is what we call asteroids. So asteroids, here you can see the planets have been formed, but you still have material which are between the planets, which are these debris, which is the asteroids, right? So, can they hit the Earth? Like I told you already, they do hit the Earth. So ever since the Earth formed, you have these things. You can see the amount of craters which are there on the Moon. On the Earth, it does not. You don't see them in that way because you have the atmosphere and you have weathering. You have various things happening due to which the craters this thing. But like I said, you have the Lunar Lake, which is there as an indicator. You already have another crater which shows you that the dinosaurs, the impact. So you do have these things happening, and basically it would have. So you could have these kind of things happening. They definitely do happen, and therefore there are various techniques in which we think of how can we actually save the earth. So in movies, science fiction movies, often they show you do a nearby nuclear explosion, you see there's an asteroid, you send a nuclear bomb and you blast it off, right? Another well-known method is it's called the gravity tractor. Basically, what you basically have to do is, if you know there's an asteroid coming in, you send another object, right, which will perturb it from its path so that it doesn't come into the path of the Earth. As long as you perturb it off, it doesn't hit the Earth. It's fine. We don't need to, blast off that asteroid as long as it's this thing. Or you could actually have a blast, you crash into the asteroid and you break it, right? So this was an experiment which was actually done by NASA, which is called the DART mission. And the DART mission, what it did was basically you had a binary asteroid, you had an asteroid called Didymos, which had Dimorphos, another asteroid going around it. So what happened, the DART mission came and impacted this. So with the idea of showing how did it actually change its orbit, right? So that then in such a case, like I said, instead of gravity tractor, you actually impact the asteroid so that it does not hit the Earth, right? So that would be some of the ways of this thing. So the DART mission was a mission which was like 4 years ago. I told you you have a binary system, Didymos and Dimorphos, and it was very interesting because they actually impacted. It crashed into Dimorphos at the speed of 6.1 kilometers, and this is the kinetic impact mitigation technique to actually see if it could deflect it. So you can see in this video, I can show you how
in a galaxy.
You actually have a video of how this the DART mission, how you actually it impacted this thing, and you can see over here, this is the DART mission, right? And it impacted here the asteroid. You can see it impacting it, and it basically was then observed from the Earth using NASA, using James Webb, using robotic telescopes on the Earth, and it was actually then followed up to see as to what happened because of the impact and how can we actually protect the Earth by a kinetic impact, right? So very interesting mission done by NASA as a precursor on how we can actually do this once you identify the asteroids. But in this, the other important job is actually to identify. So there you see the result. It actually shortened its nearly 12-hour period by half an hour, by 32 minutes when we predicted. So you can actually see it's a difficult job how they did it because this is the binary asteroids, and you can actually see how you can read about it and see how it actually was performed, right? So it actually shortened it, and that was it done. And so what happens is there are various diameter asteroids which hit the Earth, and you have a certain amount of impact energy. This is the impact energy of earlier events. This is Hiroshima bomb, but you can see that much more than that you have with Chelyabinsk and Tunguska, as well as the other bombs. Not the bombs, the asteroid impacts and the total implications, right? So, but the important bit is that you need to detect these asteroids before you do this impact business, right? So asteroids are basically detected using their shift. So if you have successive images of a patch of sky and you see that there's an object which is moving very fast, most probably that's an asteroid, okay? Because if it's a star, it's too far away, it cannot move. So look at the left picture over here. You can see here is a field of star, and I hope you can see there's an object moving. Look at this object. You can see this one is moving, right? So if you see, the stars are all still, but this object, which you can see over here, is very clearly moving. So what is done is that for a lot of this telescopic data, which is obtained from Zwicky transient factor, etc., the pan-STARRS data, that is given to Astrometrica, where these are citizen science projects, where people are basically made to inspect images obtained from these telescopes and look for bodies like this. So once you look for bodies like this, you can do some basic tests on it and you can report it that you found this object which is moving like this, right? These are citizen science projects, so these are non-professional astronomers who do it. Basically, because the number of asteroids is so large, we need a larger set of people to look for these asteroids. Once you detect it, you can send it to what is called the Minor Planet Center, and they actually check upon all these objects, whether it's a real asteroid, etc. You report it, and if it is detected as an asteroid, it is sent to the Minor Planet Center, which actually has a repository of all such minor planets, and it actually reports these objects, gives their orbit details, etc. And it goes to the International Astronomical Union, which you can have the pleasure of actually naming the object. If you were the one who detected it, then you can propose the name for it. It has to get approved by it, and therefore you may often see news items, right, where it's given to you that an asteroid was observed. For example, this one. An amateur observes to find an asteroid's moon, and this can be done even with small telescopes, even 3-inch small telescopes. You can actually find these kind of objects. So the first step is to actually detect the asteroid, and then the Minor Planet Center verifies that it is an asteroid, right? And then one can actually plan the mitigation technique based upon how much time do we have in hand, when is this going to impact the Earth, and what is the size. Most important is what is the size of the asteroid, because like I told you, if it is small, we don't need to bother. The problem is only when it's kilometer size. If it's meters, it's okay. We needn't worry too much. So often in news, you may actually see reports giving that, oh, there's an asteroid which is going to hit us and it's coming at this time or whatever. But at least with the DART mission, we know that we are at least putting some mitigation techniques in place to try to work out this thing. So that's the first thing. Let's move to the next question. The next question is, how did we actually figure out our place in the universe, right? That's a very interesting question, because when we talk about the galaxy and things like that, how did we even know that we belong to a galaxy? So let's see that a little bit. The first important thing we notice is the day and night cycle, right? You see the sun rises in a direction called east, sets in a direction called west, which we say about 12 hours. This is the basic thing which you can observe, right? Now, people did not know how to explain this. They didn't know why does this happen. And therefore, the simplistic thing which was given is that the earth goes around the sun. Sorry, rather, earlier it was expected that the sun goes around the earth, right? People also noticed there were seasons, and they noticed that the sun was in different constellations in different seasons, and that was very important because that would define how agriculture could be done, right? India, for example, is an agricultural country. You need to know the position of the sun so that you can decide when is there going to be summer, rains, winter, etc. So people would just look at which constellation the sun is when it rose, and based on that you could predict the season and do agriculture. And to note these things, what was done is there were what are called festivals. So in India, almost all the festivals are astronomical festivals because it basically marks a position in the season. For example, Holi. Holi is the beginning of summer, right? And it always comes in the same period in the year. Similarly, Diwali, etc. So based on that, the farmer could actually plan his activity and see what to sow, what to do, right? Now, when people looked up at the sky, they also saw these other objects other than stars, other than the sun rising and setting. They realized that all the stars rise and set, right? Rise in the east and set in the west. And then they observed these objects, which actually have this kind of loopy motion, do not move like the sun, and hence these were called the wanderers or the planets, right? And these were therefore, because they are moving more faster in the sky, people realized that they're closer to us. And based on this, we had the model which was given by Aristotle and Ptolemy called the geocentric model, where you have the Earth in the center, you have the planets as well as the sun, everybody going around the Earth. But then people noticed something very interesting, is that the planets had, like I showed you in the earlier thing, the planets had a loopy motion. These are called epicycles. They move back and forth. They don't move on a straight line. It's very difficult to predict their path. And that's why they were called the wanderers of the planets. Now, obviously, this was a confusing thing, that if you had the Earth and all these things going around, why do they go back and forth, right? That was not very clear. And therefore comes in Copernicus. Here you have Copernicus. And Copernicus, this is Galileo over here. You already have the coming in of the telescope 1604, and Galileo uses the telescope to actually see that Venus shows phases. Okay, he saw that Venus shows phases, as well as what we saw is that he also saw that Jupiter has satellites. Okay, that means you had some other objects going around another object other than the Earth. Others before that, it was expected that everything only goes around the Earth, nothing goes around anything else. While in this case, you had these objects which were going around, satellites going around Jupiter. And that's when Copernicus here, he proposed what was called the heliocentric theory. He said that instead of the everything going around the Earth is in blue, the sun is in yellow, and the planets have all this loopy motion. He said, let's move it to a heliocentric model where the sun is in the center, you have the Earth going around, and you have the planets going around. And for example, if this is the Earth, let's say this is Jupiter, the Earth has a smaller orbit. So the Earth moves like this. At this point, Jupiter is behind, right? But then, for example, when the Earth comes back over here, then Jupiter goes ahead. So what happens is that because the Earth has a different time period and this one has a different time period, at some point this one would be moving ahead and at some point it will move behind. So that was the explanation he gave for these epicycles. Why are the planets moving back and forth? Because they have different orbits, and in those orbits they have different speeds compared to that of the Earth. So depending on what their speeds are, they go back and forth, right? So that was the explanation given to, and what is important is in science we have something called Occam's razor. Occam's razor says that if you have an explanation which is more simpler, then it's always better to adopt the simpler explanation. So you see that this was the old model, geocentric model, in which you had to have very complicated reasons why planets are doing these strange loops, right? While the heliocentric model was a model in which you did not have to have these strange loops. You had much simpler motions for the planets, and based on that you could explain it, right? So people realized we had to move to the heliocentric model where you have the sun and you have the Earth going around the sun and you have a bunch of other planets who are also going around the sun. So you discover that you are part of something called a solar system where the sun is in the center and planets are all going around it. Now what happened is beyond this, now people notice that in the sky you see a band of light, right? You have to have a nice dark sky so that you can see it, and this is one such example. This is from Ladakh, and this is a picture by Dorje Anchuk, who works at the Indian Astronomical Observatory. He's an engineer over there, and that's a real picture by him. So people saw this bunch of stars like this, and the confusion was, what is it? Okay. Now, we already know that that is our galaxy, but obviously studying the galaxy was difficult because we already belong to the galaxy, right? So it's like looking at the galaxy from inside out. It's like you're sitting in a building, wherever you're sitting, and you're trying to build a picture of that building while you're inside. You're not allowed to go out, right? And therefore, various people try to find methods of trying to figure out what is this thing, what are the stars. So the earliest method they did was something called star gagging. That means you look in different directions and you count the number of stars. Okay, and the flux. But the one problem with this is that the flux from stars falls as 1 by r squared. So you could have a star which is bright, but because it's far away from you, the flux decreases. Now look at this. Supposing you were at position B and you look in all directions, you would approximately see equal number of stars in all directions. So you can say you're in the center of this whole cluster of stars. They're all stars around you and you are sitting somewhere in the center. Supposing you're in A, you will not see it like that. You will see more stars in one direction, less stars in the other direction. So this is the way the concept of star gagging, why people thought they could actually figure out where we belong. And here's one of the earliest images by Herschel, who actually counted stars using his telescope in 683 different directions and found this shape of this thing. Only problem with Herschel's thing was that Herschel assumed that all the stars have the same brightness. So if a star was fainter, he assumed it's further away. Okay? And based on that, he built this picture. But obviously that assumption is not correct. We have another person called Shapley, and Shapley actually is like the Copernicus of the galaxy, because what Shapley did is that he used the 60-inch telescope at Mount Wilson and he observed what are called globular clusters. Globular clusters look like this. It's a collection of stars which are clumped together very closely, and therefore it's very easy to see them because it's a whole bunch of stars. So he observed these globular clusters using the 60-inch telescope, and The interesting thing is that in globular clusters, there are stars called Cepheids. Okay? Cepheids are variable stars which pulsate. But the period of their pulsation depends upon what is called their absolute luminosity. So therefore, Cepheids are basically stars for which you can find out their distances. Okay, they are what we call standard candles. And therefore what Shapley did is he observed these globular clusters, and with that he could make a model of the galaxy based on these distances. See, in the case of Herschel, he did not know the distances. He thought the distance is just that if you're brighter, you're closer, you're fainter, you're further, right? This Shapley actually used these Cepheids to find the distances, and therefore he's the first one who got a three-dimensional picture of the galaxy. And the important thing he discovered is that the sun is not in the center. Okay, this is the center of the galaxy, which was defined by the center of the globular clusters, but the sun is kind of off the center, and he was correct in that. And one must, this thing is that Shapley's discovery is basically worked based on the work of Henrietta Leavitt, who worked on Cepheids and found them to be standard candles. We'll come back to Henrietta Leavitt later also. So you see that then people discovered a whole world of galaxies. They already realized we were part of a galaxy, right? We knew the shape. We knew our position in the galaxy. We are not in the center. And there's a world of galaxies. People observed various galaxies and this thing. So now with this, I showed you how we changed from the the Earth going around the sun and the sun being part of a galaxy, which is the Milky Way, and we are not in the center of the Milky Way. And then we see that the universe is made up of a whole world of galaxies, right? You have a whole bunch of galaxies. And therefore, from this comes our next question, question number 3. The universe is huge, and is there life elsewhere in the universe, right? So that's our question number 3. Let's start off first with planets and then with life. So the third question is, are there planets other than our solar system? So what do we say? These are called exoplanets. These are planets outside our solar system. And it's a picture of Tatooine, where you have 2, but this is science fiction. So the first step is to look for exoplanets. How do you look for exoplanets? First of all, why do we look for them? This is a very beautiful, this thing said by Carl Sagan in the book Contact, the book as well as the movie. It says that the universe is a pretty big place. If it's just us, seems like an awful waste of space. So this was the justification Carl Sagan gave for his SETI program, the Search for Extraterrestrial Intelligence, where we are basically looking for life outside the universe. Now there are various planet detection methods. There is what is called the most popular one is the transit method. There is the radial velocity method, the microlensing method. We don't have time, but just you get this thing. So the radial velocity method is very simple. You have a host star. There's an exoplanet. They are both going around their common center of mass, and therefore if you were to observe the host star and do spectroscopy, you will see that the star is actually wobbling, right? You will get a red shift as well as a blue shift, and that's basically the wobble. So basically you just need to do spectra. Look at the spectra of the star and see if you're getting a delta lambda, right? A shift in wavelength to blue and red, and based on that you can find out whether there's this thing. The good thing is, because of this you can define the orbit, you can actually find out the mass of the exoplanet also, right? Which is what you get with radial velocity. The other standard technique which is used is called transit photometry. Supposing you're observing a star and there's a planet which goes around it, obviously the star's brightness will be constant, but when the planet comes, it will fall and you'll get this, and that's transit photometry. There's another method called microlensing. It's an interesting thing that gravity can actually behave like a lens. Yeah, we know that gravity bends light, and that's what a lens does. It bends light, right? So therefore, if you have a planet and you're observing a star, you will get it's called microlensing, because the planet has a lesser mass, but it's going to behave like a lens and create a lensing effect, microlensing, with which you can detect the planet. There's also a method called direct imaging, where you actually look at the star, and generally the problem is the brightness of the star is going to be very large, so you will not be able to see the planet. Also, it could be that the planet could be very close to the star also, so you cannot see it. But if you have a method like over here, you can use like a coronagraph. Essentially, this is what happens in eclipses, right? The sun's disk is covered. But you can artificially do it with a coronagraph, block the light from the star, that's when you can actually see the planet. So this is a real direct imaging method with which you can actually observe planets going around a star. So in 2019, the Nobel Prize actually went to this team of scientists. This is Michel Mayor and Didier Queloz. These two observed the first uh, exoplanet going around a sun-like star. This was observed in 1995, and what they did is the radial velocity technique, and they detected this, and so that was the breakthrough they did. So this is the telescope which they use, Geneva Observatory. So what you're basically getting, this is the radial velocity technique which I showed you. So you'll get a shift in the spectrum, delta lambda by lambda, which is equal to V radial velocity divided by C. Only problem in this is that the shift which you've got to get is very, very small. So for example, if you were looking at Jupiter and the Sun, you will actually get the Jupiter going around at a speed of 13 meters per second, right? The wavelength shift is only 10 power minus 14 meters, which is 10 power minus 5 nanometers, okay? So therefore, that's something very, very difficult to observe, right? Earth, for example, would only give a radial velocity of 9 kilometers per second. So you can calculate what your delta lambda would be if you have 9 kilometers per second, 9 centimeters per second divided by 3 into 10 power 10 centimeters per second, and your lambda, which is again some 5 into 10 power minus 5, right? You can see that this value is going to be so small, right? And therefore, the idea is your spectroscope should be able to measure such a small delta lambda, okay? So the Espresso instrument is on the VLT. This can actually detect 10 centimeters per second. Codex instrument, which is being planned for the extremely large telescope being built by the European Union, is aiming for 2 centimeters per second. So now we'd have spectroscopes which are more and more sensitive to measure such velocities. Now the other method which I told you about is the transit method, the dip in the light. It sounds very simple, but the problem in this is that the dip in the light is very, very small, okay? Because it would be the ratio of the square of the this is the area of the star divided by the area of the planet, right? Which is r star squared divided by rp squared, right? Obviously, the planet is much, much smaller than the star, and then you have to square it further. So this is going to be a very small dip. So it's difficult to measure. But to date, we've had the Kepler and the TESS missions. These are space missions looking for exoplanets. I'm sorry I did not revise this, but now it's about 6,500. It's on 5,000, 6,500, thanks to the Kepler and TESS missions. So we actually have missions who are looking for exoplanets, the Kepler and the TESS missions, and we know already more than 6,500 exoplanets, which are already confirmed, right? Let's go to the next question. Is there intelligent life in the universe, or are the known exoplanets habitable? So for a star, very close to it is too hot, very far away it's too cold. In between, it's just right. And this is called the habitable zone or the Goldilocks zone of a star. So you can find out, if you know the temperature of the star, you can find out where is the Goldilocks zone. And you can check where is your exoplanet so that you know whether it's within the Goldilocks zone or this thing. It gets defined in different ways. Some of them define it as the region in which water is in liquid form or whatever. There are different ways of defining this. So these are a whole set of exoplanets which have been found by Kepler, and how habitable they are. And there are obviously a whole bunch of them which are habitable. The James Webb, okay, so so if you have a candidate planet which you think is habitable, one can actually use a telescope like the James Webb Space Telescope. And what can it do? It can actually see water, for example. It basically does spectroscopy with which you can identify the chemical composition on a planet. And it can actually do that and check on habitability. So that's exactly what James Webb is doing. So if you remember the first light images of James Webb, this was for an object called WASP 96b. This is not a James Webb image. This is a Kepler image which shows you the transit. But what Webb did is that it actually did spectroscopy and detected water on this exoplanet. So this was used as one of the first light images of James Webb to show the capability of James Webb, that James Webb will be able to identify water on exoplanets. There's also what is called Drake's equation, which is a very well-known equation which can actually tell you the number of technologically advanced civilizations of the Milky Way is a product of all these factors. The first is the rate of formation of stars, then the fraction of stars which have planetary systems, then the ones which have habitable these things, then on which life actually appears, then on which the life is intelligent life, and then here that intelligent life should be in a state where it can communicate, right, with other things. And obviously, an important fact is the length of time that such intelligent civilizations can exist. So, obviously, these factors are all very uncertain factors, and you can plug in all kinds of numbers in them. And so, people plug in all kinds of numbers, and with that, they get different kinds of estimates that the galaxy should at least have 1 or even 100 possible planets which are habitable. But obviously, we need to find them, and we don't know the real number. So two probably exist. Either we are alone in the universe or we are not. And here are the words of Arthur C. Clarke, where he says both are equally terrifying. Okay. Let's go to the next question, which everybody loves to talk about. What are black holes? So black holes, the theoretical defense, this thing is an area of space-time, but the gravitational field is so intense that the escape velocity is equal to the speed of light. So if you actually have such a strong gravitational force, even light cannot escape from it, right? So that is what is the definition of black holes. So just come back to what is the escape velocity. I hope you're aware of it. For the Earth, for example, 2 gm by r gives you the value of the escape velocity. It is the velocity with which if you move, you can actually escape the gravitational field of the Earth. So if you plug in numbers for the Earth, this is Newton's constant for gravitational force, this is the mass of the Earth and the radius, you will actually see that you will get a value of about 11.2 kilometers per second. Okay, that's a very large velocity. If you are at that velocity, you can actually escape the gravitational force of the Earth. So here what you're doing is you're going to put this escape velocity as equal to c, which is the velocity of light. That is the definition of a black hole. And therefore, you can also define what is called the Schwarzschild radius. This is the radius at which the escape velocity is c. And therefore, you can calculate what would be the Schwarzschild radius for example, the Milky Way. It would be something like this. If the sun were to turn into a black hole, its Schwarzschild radius would be 2.95 into 10 power 3, which is about 3,000 kilometers. If the Earth were turned into a black hole, that means all this mass was compressed, right? Its Schwarzschild radius would be 8.87 into 10 power minus 3 meters, right? It would be that small. And then these are various galaxies which have black holes in them. So, how do black holes affect the area around them? We've already, there are loads of science fiction movies and books about it, that if you actually were to enter a black hole, right, then the gravity from black hole is so dangerous only if you're close to it. If you're far away from it, you don't. Like if the sun turns into a black hole, actually life on Earth will not be affected because we are not in the Schwarzschild radius of the sun. We are further away. So the sun will actually behave like a gravitating body of exactly the same mass, and our orbit will be the same. Everything will be exactly the same. But if we are close, you can see in the video what happens. This is called spaghettification, where you can actually, the tidal friction is so strong that it will stretch out this body, right? It will become like spaghettification, and you can actually do these things, right? So you could have such a case taking place, which you can see. It's coming when it comes close to a black hole, and it actually just gets engulfed by the black hole. But while it gets engulfed, it is going to emit X-rays, okay? And therefore, if we observe in X-rays, you can actually find what is called the accretion disk. While this material is being gobbled up by the black hole, it forms what is called a disk or the accretion disk, and you will get X-rays coming out from it. So you can actually observe the X-rays, right? And we know that nature produces a variety of black holes. You could have supermassive black holes, which are there in the centers of galaxies. They have supermassive black holes. Even our galaxy has a massive black hole. 10 power 6 is there. You could have intermediate mass black holes, which are about 1,000 times the mass of the sun. Stars, if they are very, very massive, they may end up as black holes. So you could have a stellar black hole 10 times the mass of the sun. Or you could also have micro black holes. There are different kinds of black holes which are produced. Normal black holes, how are they produced? These are from the death of very massive stars. So if you have a very massive star, a massive star evolves like this. It forms from a collapsing cloud. And then if it's a sun-like star, the outer parts will go away, the core will form what is called a white dwarf. But if it's a very massive star, you'll have a supernova blast, and you'll only have the center remains, which will be a neutron star. And it's even more massive, the neutron star will be a black hole, right? So it comes by basic stellar evolution. That will actually form a black hole. By basic stellar evolution, you need a massive star, and that can form a black hole. So the supernovas actually are very interesting objects because they are very, very bright, and therefore they're easy to see in other galaxies. And they can also be used like Cepheids or standard candles because they have a fixed brightness. So they can be used to find out even distances to galaxies. They're very, very bright and you can use it. So the mass limit is the Chandrasekhar limit, and here is an example of a supernova blast in our very galaxy, which is called the Crab Nebula. And when the supernova blast took place, it was actually observable. It's there in history of observations of it. Now, like I told you, if the star is very massive, then you can actually form the outer part is thrown out, and the inner core actually condenses to a very small thing, which is massive as well as it is a very small size. It has a size of barely 10 kilometers and a very strong magnetic field. And because of the magnetic field, light cannot come out from it. So light only comes out from the poles. So what happens is this star, as it rotates, light is coming out only from the poles. So you will only see it when that light faces you. Okay? And that's why you will see pulses of radiations when the thing actually faces you. Otherwise, you won't see it. And hence, these are what are called pulsars. Okay? Where they actually, it will be bright when it only sees you. If it's even more brighter, then it won't be a pulsar, it would be a black hole. So that's how basically black holes are formed. Now we come to question number 6. What's the center of our galaxy? So the center of our galaxy, we know it's in the direction of Sagittarius. This is the constellation Sagittarius. And we know that there's a very massive black hole sitting over there, which has a mass of about 4 million solar masses. How do we know that? Is the Nobel Prize in 2020 went to this group of people. Roger Penrose basically did theoretical work on black holes, but these two people, Genzel and Guess, these people actually did observations of the black hole in the center of our galaxy. So one way of looking at it is you can look at if you look in optical light, the dust and gas doesn't let you look at the center of galaxy. But if you look in, this is in radio, you can see this is an image from in radio, and you can see we can actually look at the center of our galaxy, which is near a star called the Sagittarius A star. Okay. In X-ray also you can actually see these are X-rays surrounding the Sagittarius A star, and this is from the VLA, this image you can see over here. So what these people did is that these stars can be also observed in the infrared. So they actually observed it in the infrared using the VLT telescope, and they observed the motion of these stars. Some of them had very long periods, even 15, 20 years. This star S2 has a period of about 16 years. So you can imagine these are observations running over 16 years to actually map the orbit of this star. And you can actually use this orbit to actually find the mass of the black hole. And that's exactly what they did. It may sound simple to you, but like I said, it's many years of tedious observations and this thing to actually do it. And with that, they actually identified the position as well as the mass of this massive black hole in the center of our galaxy. So here you can see these are the different orbits which they mapped out, different stars near the galactic center, and used that. And it's crazy because these stars are moving at velocities of exceeding 5,000 kilometers per second. Okay, that's the kind of velocities they are moving with, these stars. And that's because of the influence of that massive black hole which is sitting in the center. And so it was really very great work which they did to actually find the mass of this black hole. The next question we are coming to, the 7th one, is the important one. How did the universe begin? Right? Now we'll come back to Henrietta Leavitt, because these are basically observations by Edwin Hubble. So what Edwin Hubble did is that using the Doppler effect, this is the Mount Wilson telescope again, which even Shapley used, and what they basically did on this telescope is that he observed the spectra of various galaxies. Here's Hubble looking at the spectra of galaxies. And when he looked at the spectra of galaxies, he found out the delta lambdas, the Doppler shifts. Now, the Doppler shifts actually gave him velocities for each of these galaxies. Okay. Now, what he did with this, so here's the Doppler effect. You have a source of light. If it's moving away from you, the wavelength gets stretched, it becomes redshifted. If it's moving towards you, it gets compressed, the wavelength becomes blue shifted, right? Now, you also have a cosmological redshift because of redshift taking place. And you can, what he actually did is, one minute, I'll go back. What he actually did is he measured these velocities, and he also used this to find out, and he also used Henrietta Leavitt's Cepheids. Yeah, he used the Cepheid data to find out the distances to galaxies. And therefore, he came up with Hubble's law, which you don't see over here, which is called V is equal to h into d, which is velocity of the galaxy is equal to Hubble's constant h into distance to the galaxy. Now, it's not very difficult to notice that since V is equal to h upon h into d, if you want to know the age of the distance of the universe, because you're rewinding the whole thing, you can actually see that this is 1 upon Hubble constant. So Hubble then discovered, first of all, he discovered that the universe was expanding. If a galaxy is closer, d is small, V is small, but if d is large, V is large. Okay, so that is the model of the expanding universe, right? V is equal to h into d. And from that, he could actually find the age of the universe, which is 1 upon h naught, which is Hubble's constant. So what is this expanding universe? You actually have, this is where we are. Think of this as, this is a muffin where the blueberries are the galaxies, and the space between them is basically expanding. It's not the galaxies. You and me are not expanding. The space between them is what is expanding. So you start off with the dawn of time, right? If you see over here, he made an estimate of the age of the universe, which he put as 13.6 billion years. So at the dawn of time, you start off over here, and then you have the expansion of the universe. Now, the observational thing, so one observation is Hubble's data, which is the Doppler shifts. And another very important thing in support of the expanding theory universe is called the cosmic microwave background. Okay? If such a big thing happened, which is called the Big Bang, when the expansion actually started, then the universe would have cooled down. But there should be something, right? And what was found is that wherever you look in the sky, there is a 3-degree Kelvin radiation which is available everywhere. And that is what is called the cosmic microwave background. And that is the relic which we have from the expansion of the universe. And this is an observational fact. And hence the Big Bang theory or the expanding universe theory has 2 basic supports, basically Hubble data as well as cosmic microwave background. And obviously people continue observing galaxies, and they actually, further add more precision to the value of Hubble's constant. We come to our next question number 8. What is dark matter? Now this is an interesting image. This is an image which is called the galaxy rotation curve. You know, a galaxy is made up of stars, right? So as the distance of the center from the star increases, you can actually observe stars and get their velocities. And that's what people did. You look at stars and measure their velocities. They are different distances from the center. Now what happens is, what is expected is that your gravitational force is falling as 1 by r squared, right? And therefore, as the star goes further away from the center, the gravitational force falls, and therefore the velocity should reduce. So stars closer to this thing should actually move faster, and the stars further away should actually move slower, right? So this is the expected part, which is the green curve, the falling part. That means velocity of the stars should fall as distance from the center. This is the rising part. This rising part is that supposing the center of the galaxy is like a CD, right? And all the stars are moving together, right? So what happens? All of them have the same angular velocity, right? So therefore, V is equal to omega into R. So the central part of the galaxy, where V is equal to omega into R, you can see is this straight rise, right? But this slope is nothing but omega. Omega is the angular velocity, which is a constant, and hence you will have this rising part. So the center part of the galaxy moves more like a CD or a disk, where all the stars have the same angular velocity, and V is equal to omega into R. And later on, it kind of saturates, and then it should actually fall. But what people observed is that it doesn't fall. Instead, it slightly increases, right? So the question was, how can this happen? If all the mass of the galaxy is sitting in the center, then how can all the stars which are further away still move so fast, right? And you can see that this gap was there. This is the gap which you have. Now this was actually, here you can see again, from stars they observed, they got this kind of a thing, but when you observed with 21 centimeters in radio hydrogen, you actually had this kind of rise. This is what was expected and this is what was actually observed. And one of the most important proponents of this is Vera Rubin. I also want to highlight the role played by women astronomers. That's why I told you about Henrietta Leavitt, and now I'm telling you about Vera Rubin. Now, Vera Rubin was one of the earliest, she was the one who observed these rotation curves and named this material dark matter, because this is the thing which was causing these stars to move around so fast in the outer regions. And I think this is something really very commendable, because in science, it's very good if you get results which agree with other people's results. But if you don't get results which agree with other people's results, I would say it's an ideal example of bravery of the highest kind, where you have observations, you have faith in your observations, and you stick to your results, right? Because you know that that's what you observed, and that's what you therefore think is true, and that's what Vera Rubin did. She actually proposed dark matter. Obviously, in the beginning, there was a lot of opposition to this whole theory, because this was very weird. You know, you have this dark matter which is not luminous, but you still say it's gravitationally showing its effect, and later on, obviously, more people, as they did observations, they found more dark matter. So in that way, observations support it. But when it came to proposing it, Vera Rubin, I think, is a true example of bravery of the highest kind, where you actually are brave enough to propose something which the whole world, you know, is not going to accept. So, ode to her. So that's Vera Rubin and dark matter, and there's still a lot of work happening in astronomy in the study of dark matter. We know our galaxy is also within a dark matter halo. Many galaxies are sitting within these dark matter halos, and therefore when we consider the galaxy, we have to be very important to consider the dark matter component also. Come to question number 9, which is dark energy. Now, there's a strange thing. Remember, I talked to you about supernovae being standard candles, so people can actually observe supernovae in external galaxies. Now, they knew that we have our expanding universe theory, which is V is equal to h into d, so the velocity is increasing as you move away from us. But what people found out with better readings of observing supernovae in other galaxies is that this expansion of the universe is seen to be happening with an acceleration. Okay. Now, how can you have an accelerated this thing? So this is in 1998, you had 2 independent projects. Again, they got the Nobel Prize for this, the Supernova Cosmology Project, as well as the High-Z Supernova Project. And they actually found out that there's an acceleration in the expansion. So that's the Nobel Prize in 2011, which went to these 3 people over here for their discovery. And like I said, the supernova is a powerful explosion which takes place in the final stages of the life of a very massive star. The interesting thing about that these supernovae have a typical absolute magnitude, right? On physical theory, we can actually see what should be its brightness. We observe a certain brightness, and we can use the difference in the apparent and the absolute magnitude, or the observed and the absolute luminosity of these objects, to find their distances, right? So these are what are called standard candles. I know that an object should have a certain brightness. So if I put it at different distances and I get another apparent luminosity, I can tell you what is the distance to that object. It's a very standard method used in astronomy. And what they got is that measured distances, so this is Hubble's law, velocity is equal to h into d. I'm sorry I didn't show it to you then, but here you can see it. What Hubble found, that velocity is dependent on distance. The further away the galaxy is, the more larger its velocity is. But what they found out is that with supernova data is that you actually have an acceleration. That means you actually have it moving in this way, which is the accelerated this thing. Now, how can this acceleration is something like negative gravity, right? Gravity will cause it to all come together. This is making it go away from it. And they didn't know what to call this, and hence it has been given the name dark energy. Okay? So dark energy is what is causing the expansion of the universe, and we really don't know why it is causing this accelerated expansion. But our observations tell us that this is happening. Okay, and so the observation system, it's like a negative pressure. It's not. It's just transparent, can't be done by matter, and we really don't know what is dark energy made up of. But we also have data from the WMAP. This is a spacecraft which actually was studying the cosmic microwave background, and based on this, now the composition of the universe is 63% of it is dark matter, 10% neutrinos, 15% photons, and only 12% is atoms. So therefore, that's our current estimate, where only 4.9% of the universe is ordinary matter, while dark energy is 68.3 and dark matter is 26.8. So most of the universe is dark energy and dark matter. Ordinary matter is barely 5%. That's what we are studying. And there's still lots of questions to be answered in this. And now let's go to something a little lighter. Is space tourism the future? Right? You're all aware of all the activities which are going on. Here are words of three famous people. And it's very funny when I give this talk, everybody knows who Elon Musk is. When I ask them, do you know who this is? They all say, yes, this is Elon Musk. This person is also known by people, Stephen Hawking, but many people do not know Carl Sagan. And Carl Sagan, I think, is somebody I would encourage students to read books by him, to see him. He's an astrophysicist, and you should really see his stuff. He's the person who's worth knowing. So Elon Musk says, sooner or later we must expand life beyond our little blue mud bud or go extinct. Carl Sagan says all civilizations either become spacefaring or extinct. And Stephen Hawking says, I don't think the human race will survive the next 1,000 years unless we spend space. So all these three people basically say we need to go out to space. Now, earlier what happened is space was all government stuff, right? So for example, NASA in the US was for the benefit of all mankind. And you had Vikram Sarabhai, who headed the Indian Space Research Organization, ISRO. And typically all space was basically government stuff. It was all government. But then later on, in the last decade, there was a paradigm shift made by NASA and followed by another space agencies. For example, even ISRO has a private wing now, where they decided to actually outsource their work to private companies. And that's what they actually did, outsourced it to Boeing, to SpaceX, etc., to actually do the stuff they need to do. So here you have the three people. You have Elon Musk, who starts SpaceX to basically cater to the needs of NASA. There is Richard Branson, who has the Virgin Galactic Room. And then you have Jeff Bezos, who runs Amazon, who also is part of the thing. So now you have a lot of private space companies, which are actually, the space industry would reach about 1.25 trillion by 2030. And already in 2021, it's about 15.4 billion. And lots of money being put into space industry. So Virgin Galactic, Richard Branson was amongst the first one to actually send a person out in space. So you can see over here, he had his crew members, Beth Moses and Shirisha Bandla, sitting over here. And they actually went on a flight on July 11th, 2011. This is Virgin Galactic. And he himself is 71 years old. And he was the first person to blast out on his own spaceship and go out like that. And very soon after him, that was July 11th, if you remember. And now if you see by July 21st, this is 2021, Jeff Bezos, the person who owns Amazon, he along with his brother Mark Bezos, they took the youngest person. This is a youngest person, an 18-year-old from Netherlands, and they took the oldest person, an 82-year-old aviator, Wally Funk, and they all did this space flight in 2021. So their capsule actually, it went to an altitude of about 66 miles, 106 kilometers. Okay. The definition of space is if you go above 100 kilometers, it is space. So Blue Origin went to 106 kilometers. The flight lasted 10 minutes and 10 seconds, and they already started selling tickets for actually going out to space. Now SpaceX is obviously, they did theirs in 2021 in September, that is later than these people, but what they did instead is that they did a 4-man crew, and that 4-man crew actually was out in space for 3 days in orbit, right? And they went out in space. The crew was called the Inspiration 4X crew. They went further high out, which is 575 kilometers, right? Much, much higher than this. This is even higher than the Hubble Space Telescope. And they stayed 3 days in orbit, okay? And along with this, you have a lot of space companies which are actually encouraging space tourism. So, like I said, this case you actually had space tourists going out, they're actually selling tickets, you can actually be going there. People are planning space hotels. This is obviously slightly into the future. And already you do have, I did not this thing, but they're already what are called space tourists. They are buying tickets to actually plan their trips out in space. So that's the future. There's spaces coming in more, like lots of private startups and this thing. So there are obviously many more questions which are still being there to be answered in astronomy. I just picked up 10, but I hope you enjoyed these 10. And I just thought these were a good way to show you how questions are built up and answered in astronomy and in a scientific manner. So thank you so much, and bye-bye. You could email me questions if you have.